In this lecture, we're going to start talking about the compounds that transition metals form in nature typically. Um, and so, when doing that, we get to talk about something really cool, which is that transition metals will form ionic or covalent bonds with nonmetals. And that that's like one of our first layers of we teach of like kind of like unveiling of what's really going on in chemistry. I feel like we often just teach this oversimplification early on in chemistry to students that metals and nonmetals form ionic compounds where nonmetals and nonmetals form covalent, and that really isn't necessarily the case at all. We have lots of examples of covalent style bonds between a metal and a nonmetal, and we have our ionic examples too, but we also have something in between too, which is our coordination compounds, which we'll spend a lot of time talking about. And so in general, your big takeaway from this, I think, is that typically our lower oxidation state transition metals, so things with a lower charge, like +1 or +2, they're going to form ionic compounds. And our higher oxidation state transition metals that are in the +5s, +6s, +7s, are more likely to form a covalent bond with a nonmetal and then create a polyatomic ion. Or even just focusing in really deeply on that bond, it's really just going to create a more covalent sharing of electrons, like that interaction between your two atoms has more covalent character, which can really impact the chemistry of that metal. Um, and just opens up this really amazing world of biological chemistry that takes advantage of that covalency to really tune the reactivity of that metal. And so here's two examples of this. We've got iron 2 chloride, which is that greenish, yellowish solution that you see to your left. It's just a +2 oxidation state on the iron, so one of our lower oxidation states. And it forms very much an ionic compound with the chloride ion. And then we have permanganate, which is a manganese that's in the +7 oxidation state. And it's got 4 oxygen atoms bonded to it. And instead of them being ionic in nature, they actually form something covalent that doesn't break apart when you dissolve it in water. It stays together and you get this beautiful, brilliant pink fuchsia color. And it's a polyatomic ion. That manganese and those oxygens together form a polyatomic ion, this unit right here. Let's use a different color. And so it forms an ionic compound with other metals. And so you'll see this kind of two metal picture where we have like a potassium that's providing the positive charge to the manganese oxides -1 charge. And then we've got that oxidation state of +7 on the manganese. And where part of this is coming from is that as we increase that oxidation state on our transition metal, we're actually increasing its electronegativity. That magnitude of charge is huge, and the greed or the desire, the uh, personifying elements, which is ridiculous, I know, but the electronegativity really increases with that increasing magnitude and oxidation state or charge on the metal. And so it incentivizes the sharing of electrons from that non-metal to the metal, and creates these covalent bonds in nature. Um, And so now I'm going to just kind of walk through a couple different types of transition metal compounds that you see, and looking at this difference between covalent versus non-co or ionic. So here are a couple examples with titanium. And so uh, and halides. So on the left, we've got our titanium, but thinking about halides in general. So going back to what we've learned about electrochemistry is that halides are actually really easily reduced. They're happy to gain an electron, happy to do so. And they will oxidize metals easily. They have high standard reduction potentials on our standard reduction potential table. And so we can form transition metal ions and ionic compounds by reacting them with halides through a redox reaction where electrons are pulled from the metal to the nonmetal, and form these ionic compounds like titanium chloride. And so that titanium chloride with 3 chlorines attached to it, so that titanium is in the +3 state, is going to give this beautiful violet color that you see at the top image. And then our titanium chloride that has a +4 oxidation state produces this nice light yellow color that you see below it. And while our halides tend to form more ionic compounds in general, we have really high electronegativities for our halides in general compared to our metals. And so there's going to be less of that covalent nature if we have a larger difference in our electronegativities. But titanium 4 chloride is an exception, and it's coming from that higher oxidation state on the titanium atom. And because it's a like +4 rather than a +3 or 2, it actually forms a more covalent bond and becomes kind of an exception to this ionic nature of the transition metal halide compounds in general. So those are our transition metal halide compounds. Looking at our oxides now, again, we see this trend of lower oxidation states will form ionic oxides that have an O2 minus ionically bonded to that transition metal, and that our higher oxidation states are going to form those covalent oxide compounds instead, like we saw with that manganese oxide that was covalent. Another one is like chromium oxide as well. So in general, we prepare these for that first transition metal row by heating that metal in air, and it reacts with the oxygen in the air. You could also heat up an oxalate or hydroxide and have it form an oxide from that as well, without oxygen around. And of these oxides, most of them are going to be insoluble in water. The exceptions to that are the chromium oxide and manganese oxide shown here. And we also see that oxides that are going to be with a +4 transition metal are going to end up forming amphoteric compounds, meaning they'll be able to react with water around it to accept or donate a hydrogen atom based on pH. And also just looking to the left, a lot of these oxides kind of have this white powder. So titanium oxide is kind of my go-to oxide that I think about, and it's this white chalky powder. But I wish the thing I thought of first was manganese oxide, because it's this beautiful, brilliant green powder color that's just gorgeous. And I will say gorgeous a million times in these lectures for chapter 19, because transition metals just form beautiful colors that are really exciting. So now let's talk about hydroxides and carbonates forming compounds with our transition metals. In general, when these are formed with a metal salt, if it's a hydroxide that's forming, we're going to get this kind of gelatinous precipitate as the hydroxide, but then also water molecules are coordinated to the transition metal. And here's an example right here of cobalt hydroxide. And it's kind of this, like, I guess by gelatinous, I mean, it doesn't look like a nice fine crystalline powder. It has kind of more of a goopy nature, but it is still a solid or a precipitate, a solid precipitate. But the blue color on this one, again, I'm going to say it, it's gorgeous. I love it. In general, our transition metal carbonates, and so remember, a carbonate is CO3 - 2, are going to form insoluble compounds in water.